Hi, everybody, and welcome to the week 12 video for Math 4400. So just some quick reminders. Your homework's due on Monday at midnight, and the quiz on this video is due at 8:30 on Tuesday morning before class, just like normal. So what were the key takeaways from this week? Well, on Tuesday, we saw how to apply the Gaussian integers and our knowledge about sums of squares and how they relate to factorization of the Gaussian integers to some related problems about like finding rational solutions to equations or finding Pythagorean triples. And then sort of bootstrapping off of that, we also talked about a different approach to parameterizing Pythagorean triples geometrically. And then we moved on to sort of beyond applications of Gaussian integers, but sort of some applications of some similar ideas. So first we talked about shape numbers. These were the number of dots in sort of these different diagrams of different shapes. And we talked about like square triangular numbers. And we related that to this Pell's equation, x squared minus 2y squared is equal to 1. And then sort of we saw that we could study that and understand how to produce square triangular numbers by using properties of the norm, not in the Gaussian integers, but in this sort of very similar ring z square root of 2. This is sort of just a small window onto a whole world of things, but that's sort of where we'll, about as far as we'll take these ideas, but you can sort of go much further. One thing I want to point out that we didn't talk about in class about this Pell's equation and sort of multiplying sort of units in z squared of 2 to produce new solutions of Pell's equation. When multiplying these elements that have norm 1. Is that there's also a geometric interpretation of that. So if you like sort of like this geometric interpretation of Pythagorean triples. So if you go back and you look in the textbook, you'll see something about this geometric interpretation as well, if you're curious. Okay. And then finally, we sort of finished up the week just on the last half of Thursday by going through some basic reductions for studying quadratic congruences. Basically, we just studied sort of what happens with the quadratic formula mod n, and somehow saw using that like the key thing to understand if you want to be able to solve quadratic congruences, or at least know when they have solutions, you have to understand what are the squares modulo a prime number, in particular modulo an odd prime number. Okay. So in this video, I just want to go over some basic properties of squares mod p. We started investigating this a little bit in class on Thursday, and I just want to sort of finish up that investigation. So one observation is that 0 is always a square. So 0 is 0 squared. I mean, more generally, if I sort of take any integer and I look at it mod, like as any square integer and I look at mod p, that's always a square. Like 4 is always a square mod p because it's 2 squared already is an integer. 9 is always a square mod p because 3 squared already is an integer. But in particular, 0 is always a square. And we're actually, 0 is sort of a little bit special among squares because I mean, somehow like the only square root of 0 is 0 itself. Whereas like for any other number, if it has a square root, it has 2 square roots. Like one, like that sort of like, for example, the square root of 9, like, well, there are 2 of them. There's 3, and there's also minus 3. But sort of minus 0 is still 0. So that's sort of one reason 0 is sort of a little bit special. So let's just throw away 0. And we're going to focus on understanding what are the non-zero squares. In other words, the squares in the units UP. So these are the units mod p, all the invertible elements mod p, which just means sort of all of the non-zero classes mod p. Okay, so here's a little table that we made most of in class. So here, going down the side, I have the first few prime numbers, 2, 3, 5, 7, 11, 13, 17. Then I have listed the squares in UP and the non-squares in UP. Well, in 2, from p is 2, UP is just only 1. There's in mod 2, I just have 0 and 1, and the only non-zero one is 1. And 1 is 1 squared, so that's a square. And then there are no non-squares in mod 2. This is sort of a little bit unusual. And again, we're mostly going to ignore what happens when p equals 2 and sort of also squares modulo powers of 2. We're going to focus just on sort of odd primes. So squares mod n, where n is odd. In particular, squares mod p, where p is odd, an odd prime. And so sort of you can sort of ignore this part. And then sort of where we start to see patterns is we look at what happens for odd primes. So when p is 3, 1 is a square, 2 is a non-square. When p is 5, 1 is a square, 4 is a square, 2 and 3 are non-squares. When p is 7, 1, 2, and 4 are squares, 3, 5, and 6 are squares. We computed these up through 13 in class, and I added for 17 down here. One thing to note is like if you're computing squares mod p, like if I want to sort of compute all the squares for 7 mod p, I just have to, so all the squares mod 7. Well, I only have to compute 1 squared, 2 squared, and 3 squared. The reason being that 4 squared is the same, like 4 is equal to -3, so 4 squared is -3 squared. 5 squared is -2, so 5 is -2, so 5 squared is the same as 2 squared, because when you square, that minus goes away. So you only have to go for like, if you want to compute what are all the squares, you only have to sort of just square the first half of the numbers you see, of the numbers up to p minus. So the first half numbers up to p minus 1. So the first p minus 1 over 2 numbers, and you'll get all the squares. Good, and so I mean somehow. What's sort of interesting though is like when you square each of those, you always get something different. One way to think about that, I'll say another way in a second though, is because like if you square, like if a is a squared, well, it can have at most 2 square roots, because the square roots are roots of x squared minus a is equal to, like, they're roots of x squared minus a. And so by Lagrange's theorem for polynomials, we know x squared minus a can have at most 2 roots. So somehow, like if something's a square, then sort of its only square roots are sort of whatever, like 1 square root and minus that. So somehow like that tells you that when you go through the first p minus 1 over 2 integers, like the first p minus 1, 2 integers, and compute their squares mod p, those are all going to be distinct. So not only are you sort of exhausting all the squares that way, but you're really getting distinct squares. And that explains why there are sort of p minus 1 over 2 squares in each of these lists. I'll give another explanation in a second for that. It's somehow even shorter and simpler. But good. So there are always p minus 1 over 2 squares, and so well the rest are non-squares. So everything else is there are also p minus 1 over 2 non-squares. Good, and certainly we see that in these examples. Good. So well, let me just sort of write down sort of what are the key properties, the key simple properties I want to observe right now. So the first one is what I just said, that there are p minus 1, 2 squares and p minus 1 over 2 squares in UP, and thus also p minus 1 over 2 non-squares, because that's just saying there are half of the elements of UP are square, and then sort of the other half have to be non-square. It's sort of interesting to think about what happens between the product of 2 numbers. And one thing you'll notice if you start looking at this table, like I encourage you to sort of try some examples. But if I multiply a square by a square, I get a square. Well, that's not so hard, because a squared, like a squared b squared is equal to ab squared. So that's not so surprising. What's maybe more surprising, at least less obvious, is that if I multiply a square by a non-square, then I again get a non-square. Or sort of, I can do it in either order, so non-square by square, I still get a non-square. And then if I multiply a non-square by a non-square, I get a square. So these ones are sort of maybe less obvious than the fact if I multiply a square by a square, I get a square. But if you look at this table, like if you look back at this table and sort of just try it for some of these, like, let's multiply 4 times 2 mod 11, well, that's 8, and 8 is also a non-square. Where if I multiply, like, let's try like 5 times 7 mod 13, so 5 times 7 is 35, mod 13, I get 9, and that is a square. So go ahead and check a few more on your own just to convince yourself. But we really see this pattern. So this will be quite useful. And then finally, the last property I wanted to mention is this one we've already seen when we were studying Gaussian integers and sums of squares and primes in the Gaussian integers. Is that minus 1 is a square in UP, or mod P, if and only if P is congruent to 1 mod 4. So there's a square root of minus 1 exactly when P is congruent to 1 mod 4. Okay, so We can actually justify all three of these facts basically at the same time using one simple observation. So the key thing is that we know there's a primitive root mod p. So like I can just sort of take a primitive root mod p, which means like every x in UP can be written as a to the k for exactly, let me say it this way, for exactly 1. K, so every x is some power of a, and sort of it's the power, like I can sort of choose a unique power of a, power that's between 0 and p minus 2. So each x is a to the k for exactly 1k between 0 and p minus 2. Okay, and so turns out if we just look at what this value of k is that gives us x, then that tells us whether it's a square. So if I write x is equal to a to the k, then this is going to be a square exactly when this exponent k is even. Well, one part of that is really simple, and if k is even, then a to the k is the same as a to the k over 2 squared, and this k over 2, this is an integer, so this power makes sense. So a to the k is a square. Okay, that's easy. So what about the other direction? How do you see that if a to the k is a square, that means k is even? Well, if a to the k is a square, well, it's something squared, and that something else can be written as a to the l. So a to the k is a to the l, and that's equal to a to the 2l. Well, sort of k is sort of between 0 and p to minus 2, and l is between 0 and p minus 2, but this 2l might not be between 0 and p minus 2. But I mean, what we get here from Euler's theorem, from Euler, so is that if we're getting the same thing, from Euler, from just the definition of primitive root, rather, is that if we're getting the same thing here, so if a to the k is equal to a to 2l, then k has to be congruent to 2l mod p minus 1. But that means k is sort of some multiple of p minus 1 plus 2 times l. So here, like that. This is saying k is equal to 2l plus some multiple of p minus 1. Well, 2l is even, and p minus 1 is even, because p was an odd prime. So this whole thing is even, so k had to be even. Good, so if a to the k is a square, then in fact k has to be even. We already saw if k is even, then a to the k is a square. So these are really the same thing. So, and again, somehow this is crucial. There's if you sort of take a primitive root and you write down a as x as a power of that primitive root, then sort of in terms of the exponent that appears, there's a very simple criterion to detect squares. It's just whether or not that exponent is even or not. So for example, if we want to verify this first property, that there are p minus 1 over 2 squares in UP, well, we just observe that half of the numbers from 0 to p minus 2 are even, and then for the p minus 1 over 2 non-squares, half of them are odd. So the even ones give you squares, the even powers of a gives you squares, and the odd powers of squares of k give you non-squares. So there are p minus 1 numbers between 0 and p minus 2. So p minus 1 over 2 of them are even, p minus 1 over 2 are odd. So you get p minus 1 over 2 squares and p minus 1 over 2 non-squares. If I look at this product situation, well, if I look at sort of a to the k times a to the l, that's just a to the k plus l, and sort of modulo some detail like right here to sort of bring k plus l back down to something less than p minus 2. This multiplication rule just boils down to the fact that an even plus an even is even. An even plus an odd is equal to odd plus even is odd. And an odd plus an odd is even. So this is giving you a square times a square is a square. This is giving you a non-square times a non-square is a square. This is giving you a square times a non-square, or a non-square times a square is a non-square. Okay, so that sort of verifies this multiplication property. And then finally, this fact we saw before that minus 1 is a square in UP if and only if p is congruent to 1 mod 4. Well, if you go back and you look at how you did this, the second way you did this on your homework assignment, I mean, exactly what you do is you sort of first observe that a to the p minus 1 over 2 is congruent to minus 1 mod p. But then, so the discrete logarithm of -1 is always easy to compute. It's just p minus 1 over 2. And then, well, this number p minus 1 over 2 is even. In other words, sort of by this criterion, -1 is a square mod p, exactly when p is congruent to 1 mod 4. So here I have p minus 1. If this is 3 mod 4, like if p is 3 mod 4, then p minus 1 is 2 mod 4. And when I divide it by 2, I get something that's now, if you're 3 mod 4, you're divisible by exactly 1 power of 2. And so you divide by 2, you're odd. But when you're 1 mod 4, like p minus 1 is divisible by 4. So when I sort of divide out by 1 power of 2, I still have, I'm still divisible by 2. So this is even exactly when p is congruent to 1 mod 4. Okay, and so that's the justification of these simple observations we made about squares and non-squares. Where are we going next? So next week we're going to, there are sort of some more difficult things we have to understand about squares in order to really solve this problem. So the two key properties we have left are to understand are like, when is 2 a square mod p? And then what is the relation between p being a square mod q and q being a square mod p, where p and q are both odd primes. So once we sort of have these things, then using sort of especially like this multiplicatively rule and sort of the rule for -1, we'll actually be able to put everything together, and we'll be able to give a way that lets us compute easily when any sort of number k is a square modulo prime p. And sort of the tool we use for this, the way we sort of package all these rules in like a nice computational way, it's called the Jacobi or sort of Legendre symbol. And so we'll talk about that next week. See you then.